All right, welcome to a podcast on oxidation and reduction. By the time we get done with this, I want you to be able to describe oxidation and reduction and also identify the oxidizing and reducing agents. So let's just get started here. Oxidation brings to mind what? Sounds an awful lot like oxygen, doesn't it? In fact, whenever this term was originally applied to a chemical reaction, it was just that. It was some substance that was combining with oxygen, and that was what we called oxidation. However, nowadays, that is too narrow of a definition. We're going to see an expanded definition. That expanded definition still includes the combination of a substance with oxygen, but there are other reactions that don't involve oxygen that are still oxidation. Common oxidation reactions. Burning of fuel, in fact, any kind of combustion is going to be an oxidation, and we like these reactions. We need these reactions because we get a lot of energy out of them. For instance, we use Bunsen burners in our labs. We have methane gas that combusts. It oxidizes with oxygen there, and it creates carbon dioxide and water, right, a hydrogen oxide. Bleaching, rusting, or other corrosion, these are also oxidations. Reduction is the other side of this whole equation, right? We have an oxidation. We also have a reduction. Imagine that you have some chemicals, and you have an oxide even, and you measure something about that oxide before a chemical reaction. You measure something about that after, and you find that we have a reduction that occurs. What might be reduced? Well, something we can measure is a reduction in mass. Originally, reduction was meant that the oxygen was removed from a compound. Right? So how exactly would that yield a lower mass? Well, if we think about this particular reduction reaction, the obtaining of pure copper from copper ore, we would start here with copper oxide, which you can go and mine out of the ground. You get some carbon or charcoal and heat these things up to extremely high temperatures. And what happens is that oxygen combines with the carbon to form carbon dioxide, and what's left behind is pure copper. So it's a very useful reaction, but if we were to, this stuff, this is gas, right? That's going to potentially be leaving our reaction vessel. If we were to measure the mass of our copper oxide before, maybe we had 12 grams, I don't know. Because the oxygen leaves it, I don't know, we would have less. So, I don't know, just make up a number, it doesn't matter. Maybe now we have 8 grams. So overall, the mass of the solid that we began with, after it was reduced, it's going to be lower in mass because it no longer is combined with the oxygen. Other metals are gotten from their ores this way too. Iron and aluminum are just 2 examples. You can add that heat energy you can add the energy to cause the reduction to occur either from heat. I know in the aluminum reduction process, there's typically a very high electrical current that is used in order to get that aluminum to separate from the oxygen and aluminum oxide that's in bauxite, a very common mineral, or formerly a common mineral that you could mine. The United States right now has depleted most of the high-quality bauxite mines, and therefore we're very involved with recycling of aluminum because we don't have a lot of sources of aluminum anymore. Anyway, I'm off track. Let's get back on track here. One thing about oxidation and reduction is they always occur in pairs. Right? If that oxygen is going to be leaving, it needs to be going somewhere. So the oxidation loses the oxygen. The reduction is what gains the oxygen. That's by the old definition, though. Let's consider the new definition. Right? We have atoms of element A and an atom of element B. Let's say these two are going to come together. Atom A, you can see there, has a little electron on its outermost energy level. It's one of its valence electrons. And you might recall from last semester that we talked a little bit about electronegativity. Electronegativity is the tendency of an atom to acquire electrons. Right? So it's kind of a measure of the pull of those protons in the nucleus on electrons that are nearby. Let's say, for instance, here that B is more electronegative than A. Whenever these two come together, if they come sufficiently close, there's a possibility that that electron could be transferred from A to B. Right? Notice we haven't done anything with oxygen, but by our new definition, letter A has been oxidized and letter B has been reduced. And one of the things that students struggle with is B just gained something. How is it that B was reduced whenever it gained an electron? I think one way that we can describe this that makes sense is we can consider that B started off as a neutral substance. It gained an electron, right? It gained a negatively charged particle. That would cause B to go from neutral to having a -1 charge. So if we consider the charge here, we start with a 0 and we end up with a -1. So in terms of the magnitude of our charge, by accepting an electron or electrons, the charge is reduced. So therefore B is reduced. Another way that we can remember here what's going on is this little statement, Leo the lion says grr. Right? Imagine that you just read your favorite children's book and it's about a lion named Leo and he's growling at everybody all the time. Well, Leo references the fact that losing electrons is oxidation, L-E-O. The grr part tells us that gaining electrons is reduction. So we've got Leo, we have grr. So if you can remember that, you can remember what it means to be oxidized. You can remember what it means to be reduced. Now for something that is not as fun to think about, because what you're about to hear sounds opposite. But hopefully after the explanation you'll see why this is. The substance that is oxidized, right, it is giving up electrons to the other atom. So we also call this the reducing agent. Right? It is causing the reduction of the other atom by donating an electron to it. So which substance here is the reducing agent? Is it A or is it B? Well, letter A is the reducing agent because its electron, right, had that electron here. It became oxidized. It gave its electron over here to B. B has become reduced. It caused the reduction in a sense, so therefore it is the reducing agent. The opposite of this is true. The reduced substance is considered the oxidizing agent. I highly recommend just focusing on figuring out which one is oxidized, which one is reduced, and then you can assign the other term. So once you know it's oxidized, you also know it's the reducing agent. Once you know something is reduced, you also know it's the oxidizing agent. The reduced substance is the oxidizing agent because it's taking electrons from the other atom, causing the other atom to be oxidized. And I think if you got the other one, the reducing agent is letter A, clearly the oxidizing agent is letter B. So here's just a list of how we can track the redox, which is the term that's typically used for oxidation reduction reactions. Lose electrons, that's oxidation. Still, gaining of electron is oxidation. Gaining of oxygen is oxidation. Loss of hydrogen in a covalent bond is oxidation. As we're going to see here, we'll have some rules that we'll use to assign oxidation numbers. You kind of saw a tidbit of that as I was showing the reduction in charge. We're going to expand that to allow us to see how substances are oxidized or reduced in a moment. This one's just called the reducing agent. The reduced substance gains electrons. It loses oxygen. It gains hydrogens in a covalent bond. It has a negative change in the oxidation number, and it is called the oxidizing agent. So let's talk a little bit about this oxidation number business. Oxidation numbers, here's what we're going to do with them. We're going to use these to help us figure out who's losing electrons and who's gaining electrons. So what we're going to do is we're going to follow the rules. All right? And the rules are going to look kind of nasty here. Just jot them down. You might already have them written down on a worksheet, or you might have found them in the book. I've tried to change these a little bit so they are as concise as possible while giving you all the information you need. So here they are. Blah. Write them down. An element in the elemental state is 0. I'll show you how that works in a second. Monatomic ion equals the charge on the ion. The more electronegative element in a chemical formula is negative, while that of the other is positive. Oxygen is usually -2. Hydrogen is generally +1. And whenever we add up all the oxidation numbers, they're going to add together to give us the overall charge on either the molecule or the ionic formula unit or the ion. So let's just see how we apply these instead of focusing on all the language here. Here's some examples. O2. All right? O2 is an elemental substance. Notice it's not combined with anything else. Oxygen will equal 0. And that looks like 0 equals 0, which is mathematically true, but I made sure I pointed out that oxygen equals 0 is really what that means. Aluminum 3+. That is a monatomic ion, so its oxidation number is +3. H2CO3, this gets a little bit more complicated here's what I think you should do whenever you're approaching these. You should look and see, is this an ionic compound? Well, this happens to be an acid, but it's composed of hydrogen ions and carbonate ions. So what we can do is recognize that the hydrogen, right, the hydrogen is a monatomic ion. Right? So we have H as a +1. Right? So now we can focus on the carbonate over there. Well, one of the rules that we had is that oxygen is a -2, unless it's in a peroxide. Well, this is not a peroxide. Right? It's hydrogen carbonate, it's carbonic acid. So we know that oxygen is -2. So here's the other rule we're going to apply. I have 2 times my +1 for hydrogen. So I really have a +2 from all of my hydrogens. I have a -2 for my oxygen, and I have 3 of those, so I have like a -6. And overall, there is no charge on this molecule. So carbon, the one that is the big question mark here, has to have the correct charge so that when all of these oxidation numbers of each individual atom are put together, we're going to get neutral. So what +2 and -6 will give this a charge of 0? Well, if carbon is a +4, right, a +2, +4, that's a +6, add that to -6, that gives us 0. I do want to point out here that whenever we are writing down the oxidation numbers, we write down just the oxidation number for each individual atom. Although, back here, I have considered that for each +1 hydrogen, they together contribute a +2. So when you're answering the questions on what is the oxidation number, you are going to be giving these. But to determine those, you will have to take into account the overall numbers. All right, so as you practice this more, it will become clear. Now, H2O2, this one's a peroxide, so I thought I'd throw in one that's a little bit strange. Since it's a peroxide, oxygen is -1. There's 2 of those, so we have a total of -2. So that means our hydrogens have to be a +2. There's 2 of those, so we split that in 2 equal parts, and we find that each hydrogen is a +1, just as we would expect from our rules. So to recap, here's kind of the things I would look for. I would look for first, do we have an elemental substance? Second, try to find ions. All right. Third, look for oxygens and hydrogens. And once you have done those 3 things, you're going to be down to one atom that has to have a particular oxidation number in order to either give your polyatomic ion its charge or give your neutral molecule its charge. So that's how we deal with oxidation numbers. So let's try this. Here's a particular equation. We want to know what's oxidized, what's reduced. We also want to know what is the oxidizing agent and what is the reducing agent. So why don't you pause this for just a second and come on back once you've given this a try. All right, let's see how you did. Silver nitrate. Silver nitrate is an ionic compound. Silver is, oops, let me back that up. Silver is a +1 ion. Over here in nitrate, oxygen is a -2. There are 3 of those, so that's a -6. So we need nitrogen to be a +5 for that to become neutral. Copper is an element in its elemental state, so it's 0. While we're thinking about elements in their elemental state, let's go ahead and assign silver over there. It's 0 for oxidation number. Here, copper is combined with 2 nitrate ions, so this must be the +2 version of copper. And the nitrate actually hasn't changed at all. We still have a +5, and we have a -2. So, which one is oxidized? Well, copper has gone from a 0 to a +2. In order to increase your oxidation number, you must have lost electrons. So which one's oxidized? Copper. Right? How about which one's reduced? Well, silver has gone from a +1 to a 0. So it has reduced in charge, right? It's become slightly more negative gone from a positive 1 to a 0, so it's reduced. So now that we know which one is oxidized and which one is reduced, let's figure out which one's the oxidizing agent. Well, oxidizing agent is the one that's reduced, so that's silver. Which one's the reducing agent? That's the one that's oxidized, so it's copper.